Respected guests, professors, and viewers, good morning from my side. I welcome you in this presentation on the paper Design and Construction of Savonius Rotors. My name is Mirsad Adar Shah. I completed my bachelor's from DHS Sofa University and I am currently enrolled at TU Dortmund University in Dortmund, Germany. The second author or the co-author of this paper is Dr. Samir Ali Sibiani. He is the managing director of Yanbu University College, Kingdom of Saudi Arabia. You can reach out to both of us at the email addresses listed below, so bear with me. So in this research paper, we are going to talk about Savonius rotors and their design and construction. So the table of contents are as follows. We are going to have introduction and some advantages, some research design, the working, results, conclusion, references, etc. So introduction: wind turbines versus wind rotors. As you already know, wind turbines are the collective physical thing or the physical system in which a rotor rotates. So wind turbine is the whole thing in which the rotor is encased, and rotors rotate and they convert rotational energy into electrical energy via a generator. So what are HAWTs or Hotts versus VAWTs or Watts? So Hotts versus Watts, these are the two basic types of wind turbines: horizontal axis wind turbines, or commonly referred to as Hotts, and vertical axis wind turbines, commonly referred to as Watts. So in Hotts, you can place it in any direction, and you do not you have to be direction specific. You cannot place it in any direction of the wind currents. On the other hand, in Watts, you have to put it in the direction of the wind. That is the only difference between the two types of wind turbines. What are the types of rotors? We have two basic types of rotors. There are numerous other categories of rotors. There's Savonius rotor and other types of rotors, but the two most common types of rotors are S-rotors and D-rotors. S-rotors, which are known as Savonius rotors, or D-rotors, which are known as Darius rotors, are the two basic types of rotors. We will talk about them in the later slides. But that's that. What is the Betz theorem? The Betz theorem states, Albert Betz in 1999, he was a German physicist, he put forth what is known as the Betz theorem or the Betz law. According to him, the theoretical maximum efficiency for a wind turbine is 59.3%. So all the wind current that is going to pass through or cut through the wind blades, only 59.3% of that energy is going to convert to useful work. That is known as the Betz law. And according to that law, basically, there has not been a wind turbine that has proved his law wrong. There has not been a wind turbine who has proved an efficiency of 59.3 or more. So we're going to talk about the various types of wind turbines and what parameters we can shift or change, and how that affects the power coefficient, that is the efficiency of the wind turbine. So the first is the blade shaft design. So if you want to design the blade, you have to take some factors into consideration, and you have to select a reasonable material or a suitable material that is going to be the supporting hand of your wind turbine or your rotor. So the first factor that you should take into consideration is that the blades should not break. The blades should not be decomposable over time, and the material of the blade should be easily accessible, so as you can make multiple wind turbines and make a wind farm as well from that. The cost of the material should be low. So these factors were taken into consideration, and as you already know, due to the advancement of polymers, we have designed the material PVC, or polyvinyl chloride, and that polyvinyl chloride was selected and blades were drawn from that material. So what are the important design parameters that you need to consider while designing your Savonius rotor? Those important design parameters are overlap ratio, aspect ratio, number of blades, number of stages, blade shape. We're going to discuss these in detail, but what I need you to know is all of these have been briefly discussed in the references of these papers. So if you want to discuss each and every aspect ratio or overlap ratio, you can definitely check those out, but a brief overview has been discussed in these papers. Okay, so overlap ratio is the ratio of the overlap distance, as you can see, that is D divided by, or the ratio between the diameter of the entire turbine. So E over D is your overlap ratio. As you can see in the figure below, you can see two basic figures, and the left side of the presentation denotes a S-rotor with overlap ratio, and the right side of the figure denotes an S-rotor with a zero overlap ratio. So as you can see, there is some distance between the two blades, and I can show it to you in this picture as well. So as you can see, there isn't any overlap ratio in the blade shaft, and this was taken into consideration after those papers were studied, and this is the result. So next is aspect ratio. The aspect ratio is the rotor's height to its diameter. Why this is important is because it increases its performance, the rotor's performance, and the angular speed of the rotor. As you already know from the power equation of the rotor, the more the angular speed, the more the power. That necessarily does not mean the more the efficiency, but that does mean the more the power. So angular speed is directly related or directly proportional to your your power of the wind turbine. Aspect ratio is adjusted to meet the torque and RPM requirement of the generator which will produce electricity. So aspect ratio, if you increase the aspect ratio, your power coefficient will also increase according to Blackwell. If you keep all the other parameters constant, let me remind you again, that does not necessarily mean that it will always increase, because increasing the aspect ratio sometimes decreases some other factors as well. So you have to be very careful in selecting the particular height and diameter, and a study has been done by Dr. Blackwell in his paper. You can check out his paper as well. Number of blades. So if you are increasing the number of blades of a rotor, for example, the blades that we used were 2 blades system, and if you want to use a 3 blade design or a 4 blade design, you can use it, but it has some drawbacks. According to Dr. Al-Qaim, it was stated that a 2 blade design is much better than a 3 blade system. The reason being that when one of the blades interacts with the wind currents, the other blades are not coming in contact with the wind. So the more the surface area, the more the power coefficient. That is stated in the power law as well. So number of blades don't necessarily mean the more the number of blades, the more the power, or the more the power coefficient. It only relates to having more stability, or to having more drag wasted. Number of stages. The number of stages, as you can see here, means to have one or more stage in your rotor design. So it is stated by Mr. Al-Qayyam that a two-stage S-rotor produces the best power coefficient, and he demonstrated how the power coefficient was 5% more than the two-stage power coefficient was 5% more than the single-staged one, and 9% more than, yes, 11% more than the single stage rotor. So we used a single stage rotor because it was easy to construct, and it was more easy for us to employ on the desired location. Finally, we have the blade shape, the fifth important design parameter. And let me tell you that the blade shape can change, and it can be meddled with by using some powerful tools that are available today in the market. You can use the ANSYS for the simulation of the wind currents, and you can design your own blade shapes. But we used the work of different professors from universities, and we came to the conclusion that we are going to have a simple S-rotor that we will design out of PVC, and a whole study has been done by us in this regard. You can check our paper for more results as well. But to put that in perspective, there have been different attempts to simulate different types of blade shapes and different types of S-type vertical axis wind turbine. So in a nutshell, there have been 4 attempts to simulate the different types of blade shapes. 2 of those were proposed by Kyozuka in his paper, and one of those was the Brozonius rotor, and that Brozonius rotor, which has been briefly discussed by Dr. Kyozuka. In his paper, he argued how a Brozonius rotor would perform the best in low wind current situations, but he also mentioned that when the power output will be increased, the Brozonius rotor would not be sufficient. So different types of rotors have different pros and cons. You have to choose according to your own benefits. And on the other hand, you can also read their papers and what they have to say about their papers. So this was our AutoCAD and the hardware of the blades that we designed. As you can see, there's no overlap ratio, 0 overlap ratio, and this is the base of our wind turbine. As you can see, we have simulated in AutoCAD. This just had to be on the software, and this was the final design of the prototype of the of the wind turbine. So the conclusion, as you can already conclude from it by yourself, that the design and construction of S-rotor has been briefly discussed in this paper. The design parameters were briefly overviewed with results discussed from different papers. You can check out our detailed paper as well. We have included many theories and many results from other papers as well. And finally, a hardware model had been designed according to the best design possible, which will perform best with the wind currents generated by nearby vehicles. These are the references. Thank you so much for attending the lecture. I hope to see you to collaborate with me. You have my email address, you have my teacher's email address as well. Please reach out to us. Thank you so much.